We will now look at complex conjugation. So, if then x star of n has Z transform x star of Z star. And ROC remains the same. And the proof is really simple. Trying to find the Z transform of x star of n. So, you can take the complex conjugate outside to get rid of this, because you want to relate this to the transform of x of n. But then if you do this, this is not what the previous line is. To make it equal to the previous line, you have to replace z by z star. Therefore, this by definition is what is inside the brackets is x of z star, and to account for the final complex conjugate, you have x star of z star. And therefore, now you have z star must now belong to the region of convergence, which is nothing but this. And the DT property is very simple. If you have x of z star, and if you replace z by e to the j omega, you get x of e to the minus j omega. But really you want x star of z star, therefore you have this. Therefore, this implies that x star of n has dtft x star of e to the minus j omega. And one consequence of this is, if x of n were real valued, then x of n equals x star of n. Therefore, this implies that x of z must be the same as x star of z star. And a consequence of this is that if z naught is a 0 of x of z, then x of z naught is 0, but x of z naught is the same as x star of z naught star. So this is the same as x of z naught, and this is therefore 0. Now, if you look at these two, complex conjugate both sides, therefore this becomes x of z naught star, 0 complex conjugate is 0. Therefore, this implies that z naught star is also a 0. Therefore, if the sequence is real valued, its Z transform will have poles and zeros that are complex conjugates of each other. So, this argument applies also for poles as well, because you can write x of z as p of z over q of z, and this is the same as p star of z star over q star of z star. So, this is another way of saying that if you have a real valued sequence, right, if x of n were real valued, its x of z, if it is, since we are restricting ourselves to the class of rational transfer functions. So, this is of the form p of z over q of z, and p and q are after all polynomials in z, and these polynomials will have real valued coefficients. And when you study theory of equations, if you have a polynomial that has real valued coefficients, you are guaranteed that the roots will be in complex conjugate pairs, right. So, this is another way of arriving at the same result when you know the sequence is real valued based on the property that x of z is the same as x star of z star. And for the DTFT, the corresponding property is x of e to the j omega is the same as x star of e to the minus j omega, and x of e to the j omega in general is a complex quantity as a function of omega. Therefore, this can be written as x r of e to the j omega plus j times xi of e to the j omega, where xr and xi are the real and imaginary parts of x of e to the j omega. Therefore, if you replace now x of e to the j omega by x of e to the minus j omega, you have this. Wherever omega is there, I have replaced omega by minus omega. But what we really want is, we want x star of e to the minus j omega. Therefore, x star of e to the minus j omega, now all you have to do is replace this by this, and these two have to be equal because the sequence is real. So, hence you have x r of e to the j omega to be x r of e to the minus j omega, and x I of e to the minus j omega to be minus x I of e to the minus j omega. Therefore, this is an even function and this is an odd function, and hence if you look at magnitude squared, so this is and this again is even, because square of an even function is even, square of an odd function is again even, and the angle is tan inverse xi by xr, and this is odd. The ratio of odd to even is odd, tan inverse is an odd function, therefore this is odd. Therefore, exactly mirroring what happened in the continuous time case for the Fourier transform, if you had a function that was real valued, your continuous time Fourier transform, the magnitude was even and the phase was odd, and there if you knew the transform from 0 to infinity, you knew the transform from minus infinity to plus infinity. Similarly here, because of this symmetry, if you know the transform from 0 to pi, you can complete the transform from pi to 2 pi. What is happening from pi to 2 pi is the complex conjugate of what is happening in 0 to 2 pi. So, hence knowledge of x of e to the j omega over 0 to pi is enough to specify the transform over the entire interval between minus pi and pi or 0 to 2 pi. One thing that this exponentiation, the modulation example I had shown here, typically this is given by this block diagram. So, you have x of n and you have e to the j omega n, and this is y of n, and this modulator is a linear system. This is time variant because of the time varying gain.